So let's take a look at this one more time. So the response of the system is given by this equation, which is a function of time, and time appears in only one place here, except for this step function. But this step function is constant for all positive values of t, so you don't need to worry about that. So for all positive t values, this is 1, and the only changing term is this t term. So to make the analysis simpler, I call the inverse is this tau, so that the function becomes e to power minus t over tau. So now I can easily calculate what happens to the output at different time values, and I can give time in terms of tau. So for t is equal to tau, I have minus 1 here. For t is equal to 2 tau, this becomes minus 2. And in the end, the output changes according to the what you see here. So for t is equal to tau, the output becomes the steady value of the speed times e to power 1 minus e to power minus 1. So this part keeps changing as I change t in terms of tau. And as you see, as t gets larger, this becomes smaller and smaller, right? Because this is e to power minus something, and that minus something grows. As that minus something grows, this term approaches 0. And you see that from these results. For t is equal to tau, the speed is 63% of the steady speed. At t is equal to 2 tau, speed is at 86% of the steady speed. That means the speed changes according to this graph, right? It slowly or asymptotically approaches the steady value. So to make this complete, I can mark these. So this is 0.63. And I call this VSS. This is then 0.63 VSS. And this is, I think this was 86. This was 95. Okay, so the how fast car accelerates depends on tau. Okay? So this graph is in terms of tau. So I can see that the car reaches 98% of final speed in 4 tau values. So if okay, so let's now consider some numerical values. Okay, so that tau parameter we defined as m over b is in fact called the time constant of the system. So we will talk more about that in our upcoming lectures. So let's assume these numerical values. Let's assume that the mass of the car is 1,000 kilograms. This KE parameter, which the transfer function of the car is 12,500. This should be newtons, right? And let the B parameter be 250 newtons per meter per second, right? So the unit for the B parameter has to be force divided by speed, right? So the unit is in SI unit system newtons per meter per second. Okay, so by using these numerical values, we see that the steady speed of the car is given by this much. And if theta 0 is equal to 1, which means we apply the full gas input to the car, then the steady value of the speed of the car can be found as 50 meters per second. Which corresponds to 180 kilometers per hour. For example, if you apply half the gas pedal input, then this number is going to be half of that, right? Because the theta 0 parameter is right there. So if you insert half of the previous value, then this value will be okay. And what's really important here is the tau parameter, because that determines how fast the car reaches that final speed. And for these numerical values, the value of the tau turns out to be 4 seconds. So this was defined as mass of the car divided by d, but mass is chosen as 1000 kilograms, and b is 250 newtons per meters per second. But Newton is equal to kilograms times meter or second square. So these kilograms cancel each other out, and these meters also cancel each other out, and that goes with that. And in the end we find the tau as 4 seconds. So the unit of that is seconds, so that's why we call this time constant. Okay, so it's 4 seconds. So if we go back to the previous graph here, so we see that the car reaches 98% of its final speed in 4 time constant, which is equal to 16 seconds. Okay? Okay, now let me go to MATLAB and do all these things in MATLAB. So I define these numerical values, I write them here. I define GE, which is the transfer function for this block. That is just a constant number, right? So here's how I define it. So it's a transfer function. Normally here, if you remember, I write the coefficients of numerator polynomial and the denominator polynomial. The numerator polynomial has just a constant number, which is KE, and there's no denominator, right? Or the denominator is also a constant number. So this is how I define the GE transfer function. The car transfer function is 1 over ms plus b, a constant number, and on denominator I have a first order polynomial with 2 coefficients m and b. So this is how I write it, m and b. So this defines the transfer function for the car. And I want to simulate it for 25 seconds. I want to see the response between 0 and 25 seconds. Input, this is the step input. And I choose theta 0 as 0.5. So I use a gas pedal position of 1 over 2. So this is my theta 0. I put it right there. So the gas pedal input is T0 times U. This is the unit step function again, and this is the magnitude of the step. Okay, and I want to plot the input. So this is the input applied to the car, to the gas pedal. And the response of the car, I directly use the MATLAB LSIM commands. Okay, so I know that the output is given by this expression. So this gives the output of the car. But instead of using this function, I generate the outputs by using the MATLAB LSIM commands. So to make the two compatible, GE is what I call KE here. So maybe I should fix it here. Okay, so this is what I simulate there. The following command. Şimdi G yapayım da şey olmasın. So let me make this bigger. So this theta is for the input we applied. So this is equal to that. So that corresponds to that, and it just gives me the output. And the result is saved in a variable named y. Okay, and then with the command plot t, y, I can plot the output. Okay, so this is the result. The gas pedal input is a constant input with magnitude 0.5, and the speed of the car changes according to the graph you see here. So let me put some grids here. So the speed of the car should reach 25 meters per second, which is almost there. As you see, 25 goes to 25. And so according to our calculations before, it should reach the 63% of the steady state value in 4 seconds, right? So let me just check that if that is true. So first let me calculate what 62% of 25 is. So at 4 seconds, the speed of the car should be at this value. So the 4 seconds is here. Well, it's not quite there, but that's because of the what's that? The rounding, I guess we did. So instead of 63, it should be 25 times 1 minus e to power minus 1. Yeah, this is the real value we expect to get, and this is in fact what we see here, right? Yeah, at 4 seconds, indeed at 15.8 meters per second. Okay? So this was a simple problem, but let's see what we did here. So let's go back to the beginning of the lecture. So it's a very simple block diagram with only 2 blocks. In fact, one of the blocks has a first order transfer function. The other block is just a constant number. So from here we obtain the overall transfer function as the multiplication of the 2. And when we give an input, we found the output function, and then by plotting that function, this is the final result we get. Okay, so the car starts accelerating and keeps accelerating up until it reaches a steady value of 25 meters per second. Okay? Do you have any questions? Okay, so at this point we can try a few more things. For example, we can start changing the parameters. So one obvious parameter is the mass of the car, right? So let's see what happens if you put some load into the car. So suppose that the car is loaded with, 500 kilograms of load. So let me just change the mass. So let me plot it into the second figure so it doesn't overwrite the first one. Okay, so if I change the mass, what do you expect to change? Just look at this equation. So do you expect the final speed to change? Not really, right? Because the final speed is given by this part and there's no mass in that term. Mass only appears here, so the mass changes the time constant. Okay, so if I increase the mass by a factor of 1 or 1.5, so that makes the time constant 6 seconds. So let me just bunu şey yapalım ya, aynı şeyde çizsin, farklı bir renkte daha güzel olacak. O zaman şöyle yapacağız. Okay, so now let me change the mass value to this much. The new transfer function of the car is this, G car. So I need to simulate it one more time. So let me call it Y2. So let me make this red. Okay. Evet arkadaşlar, gördüğünüz gibi arabanın son hızı değişmedi. Sadece time constant'ı değişti. Time constant 4 saniyede 6 saniyeye çıktı. Dolayısıyla bunun 4 saniyede ulaştığı hızda kırmızı 8 saniyede ulaşıyor olması lazım. 6 saniyede pardon. So let's check that. this seems to be right? So the blue one reaches this speed in 4 seconds, but the red one reaches the same speed at 6 seconds. So which is consistent with our equations. Peki gerçekte öyle olur mu sizce? Yani arabayı yükledikçe son hız değişmez mi?
Değişir.
Niye değişir? Yol sürtünmesinden değişir değil mi? Yani yol sürtünmesi biliyorsun normal force ile alakalı. Arabanın ağırlığının arttığında normal force arttığı için sürtünmeden dolayı son hızı değişir arabanın. Ama tabii biz onu burada görmüyoruz. Çünkü biz sürtünmeyi modellemedik. Burada sadece viscous friction modelledik. O da sadece şeye bağlı. Ne derler? Hıza bağlı. Yani aslında şuradaki şimdi bu denklemler açısından düşünecek olursak tepeye gidelim. So this is our viscous friction term, right? So normally this B coefficient should depend on the weight of the car. Should depend on the normal force, and normal force is the weight of the car, right? So now let me change that as well and see what happens. Let me change the B number. Let me multiply this with the same. It is also increased 50%, and let's see what happens now. Okay, so this is a more realistic situation. So the final speed of the car is now less compared to the previous one. Okay. So I would like to show you one more simulation. In the above, we assumed a static engine. Let's try a dynamic engine. In this case, instead of a constant number, engine transfer function GE should be a rational function of S. So before I use this, G is equal to KE. Now let me use G is equal to KE over S plus PE. Let me use this engine model. Okay? So this is the first order engine, dynamic engine model. There's a single pole at minus PE. And let this PE be 1. Okay, so let's try 1. Okay, so now this is the good thing about using this block diagram. In fact, right now we see the benefit of that immediately. I'm just replacing this block, right? I'm replacing the transfer function for that. So in the code, here's how I can do it. So previously, this is how I defined the engine transfer function. Okay, so I'm taking this mass back to the original value. So I'm going to change this part. So this is a dynamic model. So instead of as a constant number, I have a denominator as well. And that denominator is 1 and 1. Okay? And that's because I have a first order polynomial. The coefficient of S is 1 and P is chosen as 1. Now let me simulate it and see the results. Okay, so this is the red one is the new response. So this blue one is response with static engine model. The red one is the response with dynamic engine. Bu da beklediğiniz bir şey değil mi? Yani öbüründe gaza basar basmaz bir kuvvet ortaya çıkıyordu. Şimdi gaza basınca kuvvet biraz gecikmeli olarak ortaya çıkıyor. Çünkü dinamik bir model var. Yani bunlar aslında şu iki şeye karşılık geliyor. Yani birisinde şuydu, direkt böyle motor öyle tepki veriyordu. İkincisinde böyle biraz gecikmeyle motor kuvveti takip ediyor. Bunun etkisini direkt şeyde görüyoruz. So we see the direct effect of engine dynamics on the overall response. If we change, so the car takes more time to reach the same speed. Okay, so let's move on to the next case. Next, I think we're going to look at what happens if there's a disturbance force. We didn't check that before, right? Or okay, so this is how we proceed. Okay, so now let's think about the control problem. So remember, in control, I told you that there's an output we want to reach, and we need to find the inputs to reach that output. Okay, so now let's assume for the moment that we have our system, and we studied the system. We found the response of the system to a unit step input as given by this function. Okay, and now based on this equation, suppose that we want to find the input to this system, and our target speed is 25 meters per second. Okay, so we want this car to drive at a constant speed of 25 meters per second. So we want the steady speed to be 25. Now let's think about the control problem. We have the equation and transfer function for our system. Suppose that we want to reach a constant steady speed of 25 meters per second. So let's also say that the input is a step function, and we just want to find the magnitude of the step input, which is theta 0. So VSS is equal to this parameter, right? So the desired speed is 25. So theta 0 can be solved very easily from here. B times VSS desired in fact from here we know what this is going to be, right? It's going to be 1 over 2. Okay, so we find that if you want to reach 25 meters per second, then the input pedal position should be half of the maximum deflection available. Okay, so this is in fact a control solution, right? So the control solution here now tells us that if you apply half the gas pedal position, your car will reach 25 meters per second. So the solution gives above as theta 0 is equal to 1 over 2. So we already know that a step input with magnitude causes the car to reach a steady speed of 25 meters per second. But this is so if the car equation is really given by this equation, right? Or if the car transfer function is exactly equal to this transfer function. Bunu da G yaptığımıza göre onu da değiştirelim. Okay, now, so, but what if our equations were not accurate? It's a question. Bu soru işareti deyince şimdi bu yeni nesil, benim oğlum da çok onun bir şey örneği. Böyle her şeyin kolayına kaçmayı çalışıyor insanlar. Yani herkes değil tabi de genelde böyle bir şey var gibi gözlemliyorum. Yani ne bekleniyorsa onu yapayım yeter. Yani biz hayatta mesela oğlana yapması gerekenden fazla bir şey yaptıramıyoruz. Neyse. Mesela işte ödev veriyor. İşte bunu da işte isterseniz yapın. İşte onu yap istemiyorum diyor. Hoca isterseniz yapın dedi diyor. İstemiyorum. Bu şeyi de çok duymuştum. Mesela bu soru işaretlerini falan ürünler. İşte bir dönem onu çalışıyorlar. İşte bir paragraf veriliyor. Boş yerler bırakılıyor. Boş bırakılan yerleri noktalama işaretleri koyun. İşte nokta, virgül neyse soru işareti. Soru işaretlenirken ödev vermişler. İşte örnek soru cümlesi yazın. Bizimkinin yazdığı soru cümlesi bu ne? Yani 4 karakterden oluşan. Yani bir şey de diyemiyorsun. O biraz daha güzel bir cümle yazıyor. Daha böyle. Ama işte soru cümlesi neticede soru işaretinin kullanımına ne derler? Doğru bir şey. Neyse. Şimdi tekrar konuya dönecek olursak. So what I do here is I know that the car transfer function is given by this GE times G, and based on this equation I find the input magnitude I should give to the car. Okay, and this was 1 over 2. But I'm trying to show you that this is not a good way of controlling a system. And to convince you of that, I want to show you this case. The case where the equations were not correct. For example, in our equations, we assumed that the engine was, and the numerical value was, I think, this much. Let's assume that the engine performance is less than that, and the real KE is equal to 10,000, for example. So for example, you can think of it as the engine is not working in its optimum conditions, right? It needs servicing, for example. Okay, now if we apply an input with so I'm going to use the same relation again because nothing has changed. Only the value of this numerical value changed, right? So this is the real, and I should use the real value for that KE. Kaç olacak bu? I think it's going to be 20, right? 20 meters per second. So when choosing the input magnitude as 1/2, we were expecting a final speed of 25 meters per second. But if the engine performance is less than what we expect, this causes the final speed to be less than what we expect, right? So based on our model, we were expecting to reach this to be our final speed, but if the engine performance is less than what we expect it to be, this causes the final speed to be less than what we expect it to be. Okay, so this is obviously not a good result. So if we want to reach the final certain performance, certain output, then we want to be able to reach that final performance, even if there are some problems in the system, even if there are some such minor problems in the problem. Okay, so let's consider another scenario where the model of the car is accurate, but there is an external disturbance acting on the car. Suppose that the car is climbing a hill, okay, so now suppose that we're driving uphill as shown here. Okay, so in this case, there's going to be a component of the weight of the car trying to slow it down, right? So normally we had the weight of the car like that, let me call this W. But in this case, a part of that force is acting in the axis of our motion, right? So we're going perpendicular to the road or parallel to the road. Now in this case, we have this force due to the weight trying to slow the car down, okay? Okay, so for this case, the disturbance force is now that much, and that alpha here is the inclination of the road. So in addition to the gas pedal input, there is now a disturbance input. So if the inclination is constant, then the disturbance input will be constant as well. And this input is constant with magnitudes. Okay, so that's the magnitude. So how do you find the speed of the car? I need to go back to this transfer function for transfer function matrix. Şunu da yazalım mı, sonra burada bırakalım. Ya da direkt son halini yazayım ben. We can also take this G out of the parentheses, right? So let me do that as well. So let's assume the static engine again. If G is equal to KE, and this part is going to be okay. So let me just stop here, and I will continue from here tomorrow.
Is there